Hi, I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. Today I wanted to talk about transfer functions when we are deriving it from a circuit, and then also we want to look at plotting what is called the Bode plots. So our goal today is to analyze this circuit first to achieve the transfer function. So as you know before, that you are going to replace the time domain elements into a frequency domain, analyze the circuit in the frequency, and then transfer back into the time domain. So our first thing is that transformation, and if you recall, it's 1 over j omega c. So there are two ways to plot things in the frequency domain. So when we've plotted them in the past, we have looked at the imaginary versus the real. And we can plot that as either in the Cartesian form or in a polar form. So we can get usually a vector is what we usually look at. So there's another way in this frequency domain which we use to mathematically solve any of these complex circuits. And what we can do is just note the location by an x of the end of a vector. And this is called the S-plane. And so when we solve things in the S-plane, we are going to replace that j omega with s equal to j omega. So that means that this becomes then 1 over sc. So analyzing this, we want to find the voltage here. And we're going to treat this as a polar form of V1. And so that will be the phasor of V1. And so analyzing this, we see that these two are in parallel. The C1 is in parallel with the R2. So we could make an equivalent, R equivalent, as 1 over SC in parallel with 10, which simplified would be we can get a common denominator, and that would mean we would multiply a common denominator on the top. And this puts an SC in the top for that one. And we can then, these would cancel out, so we would 10 on the top divided by 10 SC plus 1. And then we can then see that this is a voltage divider, and so our V is going to equal V1 times that R equivalent over R equivalent plus 40. And to get the transfer function, remember it's going to be the output, which in this case is this V, over our input. And so to do that, we just divide by our input here. And so that leaves us with this R equivalent over R equivalent plus 40. And if we plug in R equivalent and do a little bit more math evaluation, we can reduce this down to look like 1 over 5 times 1 plus S. And so replacing in that C equal to 125 milli, that will reduce down to this equation. So we typically call this an H of S function, which stands for the transfer function, that output over the input in terms of S. So now we have a equation, and we want to look at graphing this for its magnitude and its phase, just because in the polar form you're going to have both of those components. So we're going to change back to the j omega. And then look at also, we want to know over all frequencies what happens to this circuit. So in the past, we've looked at analyzing it for one specific frequency at omega. So now we kind of want to look at the response over a whole lot of different omegas. What happens to these circuits? So to plug this in, we're going to put in j omega. And so we get an h of j omega is equal to 1 over 5 times 1 plus j omega. And recall that when we take a magnitude of a number, say a plus bj, that's going to be the square root of the real squared plus the imaginary coefficient squared. And when we take the phase, that is the inverse tangent of the imaginary coefficient over the real coefficient. So plugging that in, or doing this for hj omega, so if we take the magnitude, we're going to take the magnitude of the whole quantity, which means the magnitude of 1 on the top is going to still stay 1. And then if we have any components, we know that the magnitude of each of those components can be multiplied together. So we can separate the magnitudes. So we could take the magnitude of 5 and multiply it by the magnitude of 1 plus j omega. So in that case, it would be 1 over 5 times the square root of this magnitude, which is 1 squared plus omega squared. And now we have the magnitude as a function of omega. So we could make a plot here of omega with omega being different values. So we could put in omega equals 0.01 and get a value for the magnitude at j 0.001 and so on. So for every frequency we can get a plot or 1 point, and then we can combine them to create a continuous graph of all of the magnitude. So the other component that we're interested in is that phase. So looking at the phase, we're going to take the phase of hj omega. And so that is the phase of the whole equation. And so again, that we can take the phases, we would take the angle of 1, which is a real, so that's going to be 0. The angle of the 5, and then the angle of 1 plus j omega. And we recall that the angles, when they're multiplied, add up together. So instead of multiplying them, we would have an addition. And angles that are on the denominator of an equation become a subtraction. So we would take the angle of 1 minus the angle of the 5 minus the angle of 1 plus j omega. And the angle of 1 is going to be 0. The angle of the 5, again, is just a real number, so it's going to be 0. And the angle of this is going to be the inverse tangent of the imaginary coefficient, in this case, which is omega, over 1. And so again, we can plug in omega equals 0.001, and then we would take that the angle of hj 0.001 is going to be that minus inverse tangent of 0.001 over 1. And we can get an actual value for that. Put it on a plot for every omega that we find. We would put a dot on the degree axis. And then we could combine all of those dots to create a continuous graph. So I don't want to do this by hand, so I took this to MATLAB, or Excel can also be used, and you can plot this. And I got let me back up 1 second. So on the magnitude plot, we're going to take the dB value. So remember that the dB value is the 20 log base 10 of whatever value we have. So this would be our quantity that we find. So for example, when we calculate this value out, which would be 1 over 5 times the square root of 1 squared plus 0.001 squared. We are going to get a number for that. We take that number, and that is the number that we put into this location, and take 20 log of that. So on this is called a semi-log graph. And so the axis on the x-axis, which is going to be our mega, and this is in radians per second. So these go by 10. So we can't have a log of 0, so we usually start at really low numbers. So we could start at 0.001 as an example, or some other number. So if we wanted to, we could start at 0.01, and then each of the lines is going to be a decade, meaning by 10. So from 0.01 we go to 0.1, the next would be 1, this next one would be 10, this next one would be 100, next one would be 1K. So it's a multiplication of 10 along each of those lines that have the larger gap between them. So between here and here, this would be 0.2. This next one would be 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Then you would get to 1. And then it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then they would jump by tens, 10, 20, 30, 40, 50, 60, 70, 80, 90. And then you would get to 100. Then it would be 200. So you can find any value in between there when you want to do this plot. So I already know what this graph looks like. And so each of these values was plugged into MATLAB or Excel, and I got a point at each one of these. So there was different points at each value in here. And then I can connect those to create that continuous graph, and it ends up looking like this, where it's flat. Doesn't look very flat. It's flat until it reaches at about 1, and then it starts to roll off. And it keeps going down and falls off like that. And our phase is going to be similar in that we have now degrees as our y value. And again, it's omega in radians per second. And this was a 1.1, 10, 100, and 1K. And this plot ended up looking approximately like this. So it came in and it goes down like this. So this was kind of the approximate form of this graph. All right, this concludes this example. Thank you for watching.